Okay, so I'm going to talk about something I've been working on for the last 3 years here at Michigan-Dearborn, all about using the Hubble Space Telescope as a new way to probe what a thing called the Milky Way bulge is doing and how we think it formed and developed. So you can see the bulge if you look out on a clear night in the southern hemisphere. It's this sort of bulge that literally rises out of the plane of the galaxy. And before I get too far with this, I do want to acknowledge my colleagues, in particular, thanks to Castle and the Startup Fund for Natural Sciences for funding part of this, and also some of the students in my research group for helpful discussions. So back to the bulge. Bulges play a literally central role in the formation and development of structure in the universe, and therefore in the way that elements are recycled in the cosmos. The video on your left is showing a simulation for the formation of a Milky Way type galaxy in a cosmological context. Here's gas being pulled in, stars are developing. On the top right is a figure to motivate this idea that bulges are sort of lurking with intent in the formation of galaxies. It's showing you from the literature the way that the stars in the bulge move, this sort of size of their dispersion, against the mass of the black hole in the center of the galaxy. And although it's become more interesting since it's been recognized that there are two kinds of bulge, it's pretty clear that bulges are important for understanding structure in the universe. The problem is that we're inside the Milky Way galaxy, so although our bulge is by far the closest to the sun, we're looking at it through the intervening material. So on your left is a figure showing what we think the Milky Way might look like could you see it from the outside. It's Milky Way analog NGC 4394. On the right is what we actually observe for our galaxy. This is one of the Hubble images I've been talking about, and we're looking down a sight line that passes right through the foreground disk towards the bulge that we care about. Now, it turns out that if you have a nice, accurate detector, such as the Hubble Space Telescope, you can isolate bulge stars from the foreground. In fact, we showed back in 2008 that even with a 2-year time baseline is enough, so a 2-year separation between epoch 1 and epoch 2 is enough to watch those foreground stars move in front of the bulge. It's a little bit like looking out of a train window as the foreground moves ahead of the background. But by the standards of modern astrometry with Hubble, this measurement, which is roughly equivalent to watching a tennis ball move by its own diameter in a year as seen from Dearborn in Los Angeles, is not actually stretching Hubble to its limit anymore. And so back in 2008, we thought, well, can we do better than this? Can we actually chart the way that the star's motions vary with distance? And what if someone comes up with a way to tag them by chemical abundance as well? That's what I'm talking about today. So since our 08 paper, a project with Hubble was carried out to actually chemically tag about 250,000 objects in this field of view, using a special set of filter combinations, really, to turn the Hubble imager into a spectrograph. What you're seeing here is the division of the stars in the Hubble field of view, that's the image on the right here, into a metal-rich or a metal-poor sample of stars. We borrow some techniques from machine learning that are extended to handle very strongly varying measurement uncertainty and apply them in this case. I can talk about these figures at the bottom if anybody asks me. I probably don't have time to do it right now. In a nutshell, though, we have a metal-rich and a metal-poor component that we've let the data drive us as to where they are. So in some sense, this is a data-driven approach. When we then ask how do these things move, so we're saying we take the apparent sideways motion of the stars and ask how does that vary with distance from us to the stars themselves. We find that we can draw quite clearly the rotation curve of the bulge dissected into metal-rich and metal-poor stars. And we clearly see a difference in the way that the metal-rich stars move versus the metal-poor. This is tracking from near the sun to far away from the sun. And the metal-rich stars show first off, a larger amplitude switch from the near side to the far side in the way the velocities work. It also turns out metal-rich stars show more organized motion. So this is our main result. The metal poor and metal rich populations definitively move differently in the galactic bulge. That's important because this is actually quite controversial. The figure on the top left is showing you what happens if, instead of looking at stars progressively along a narrow sight line from the near to the far side of the galaxy, you instead take a sort of fan beam approach and say everything here, everything here, everything here, track across the galaxy. When they did this with the traces they were using, in this graph the red is metal rich, the black is metal poor, that test was not sensitive to this. We are. And so this is just the tip of the iceberg. Recent evolution of this field is now suggesting that indeed we think that multiple populations are present within our own galactic bulge that we think formed at slightly different times in the past, some as recently as 5 billion years, some closer to 10 billion years ago. And as the bulge develops and evolves, we should see kinematic signatures, just like we're finding here. The lower left figure is another example of this, where you can ask, instead of what is the bulk motion, what is the spread of motions? And indeed, there's this fingerprint of more metal poor, possibly older, showing more disordered motion. And so our results are entirely consistent with that. Here's another figure showing you, now from the point of view of the age of the objects, when do we think these stars formed? And in this figure, the red and the blue roughly correspond to our red and blue over here. So we think the metal-rich stars may have formed more recently, metal-poor formed more for a longer time in the past, and that's why their velocities have kind of smeared out over time. So what's next? One nice thing about this approach, using Hubble to really dig deep, is that it opens up a whole new sort of observational iceberg, that's the blue, beneath the tip, which is the giants, that's the red, that are more typically used to do traces. The kind of objects we're now looking at, they're vastly more common on the sky than other giants that are more typically used. And so what I want to do next is to then extend these techniques to actually track 4 different sight lines from the same data set that we've used to develop the method as just one. The idea, just in a nutshell, this figure on the right is showing you 2 simulations, or 2 figures from a simulation, showing where these modelers think the metal poor stars, that's the top panel, and the metal rich stars, that's the bottom panel, might be found if you were to look down on our galaxy on the inner edge. In this figure, the red stars are oldest and the blue are youngest. So what I want to do next is to apply this new technique to observe trends across this thing and really compare this in detail with models for how the Milky Way bulge formed. So in a nutshell, that's about it. Watch this space. I'm hoping to get this. This is now with collaborators before submission to a journal, so I'm hoping this will appear in print before too long. And yeah, it looks like a promising technique. Thank you.